everyone, and welcome back to 6.5. We're talking about the inverse trig functions, and in this video we are going to talk about the inverse cosine curve and what it looks like. I will probably also get to the inverse tangent function, possibly depending, and because I feel this will go a little bit faster than the last one, simply because we've already done some of the groundwork, so you kind of know what we're going to be doing. So we're going to start with that cosine curve. And the cosine curve starts up here and goes, looks like that. So there's our y equals cosine. And it goes through its complete cycle in 2 pi, goes halfway, there's pi, here's pi over 2, 3 pi over 2, there's our negative pi over 2. And again, in order to talk about a inverse, we need to restrict where we look. So we're going to restrict this function. Again, we're looking for a section of the curve that covers the entire range, so we can make sure we get all of them in here. Just a reminder here, and to be complete, the domain of the cosine curve is negative infinity to infinity, our range, negative 1 to 1. So we want to make sure to cover everything from negative 1 to 1. And where they've chosen is this region right here. So we're going to restrict looking to just negative from 0 to pi. So if you're thinking about where your angles are, we're just looking in that first or second quadrant. I'm going to draw the curves first of all. So here is my point 0, 1. And here's my point pi over 2, 0. Kind of. And there's my point pi, so this would be pi negative 1. And if we can remember, this is going to switch our x and y's around. So here we're restricting. This is still the cosine curve, but we're restricting the domain to just go from 0 to pi, but our range still takes on all the values from negative 1 to 1. So now we're going to draw that inverse function. Oops, inverse cosine. Okay, so we put a little minus 1 inside there. That's going to be switching our domain and our range around. So our domain, thinking that's going to be our ratios of our sides, adjacent over hypotenuse, and the range is going to kick out the angles, but the angles it kicks out are from 0 to pi. Okay, so now I need to flip this around, so 1, 0, and 1 is smaller than pi over 2. Pi over 2 is about 1.57, so this is going to be the point 1, 0. This point here is going to be 0 pi over 2, so 0 pi over 2 is going to be here, because pi over 2 is larger than 1. And I have to try to remember how this looks. I always do a bad job of that. And this is going to be then pi negative 1, so it's going to be negative 1, and I'm up here at pi. And the way this is going to look something like that. Very roughly speaking. It kind of will look like a sine curve or a cosine curve going up the y-axis somewhat. And I probably have them shifted. Maybe it does this sort of thing. I'd have to put in more points. Probably does that, the dotted line. But it kind of looks like that. Roughly speaking, again, it's just to get you feeling for what it does. I'm not going to make you to draw these inverse cosine curves. I really wanted to draw the curves more so that you get an understanding of why we restrict it the way we do. So we can actually ask ourselves questions like, what is the inverse cosine of something? I do want to make a point though first, before I do any further, is I want to remind you that this cosine -1 does not mean 1 over. Okay, so this is not an exponent. This is something that Newton decided he wanted to use in his notation. It does not mean 1 over. It is not an exponent on the cosine curve, because we know that 1 over cosine really is secant. And our inverse function is giving us angles. So it's giving us an angle measurement, and the secant function gives us another ratio. So they are not the same. So let's practice our inverse cosine. And let's just do a couple, and then we'll talk about what the inverse tangent function looks like. And let's look at the inverse cosine of a -1/2. Okay, and remembering all of our pieces. So this means we're looking for where in the world is our cosine function a -1/2. Now our inverse cosine function is going to give us angle measurements between 0 and pi. So first quadrant or second quadrant. Cosine being negative is in the second quadrant. Cosine is our adjacent over hypotenuse. So adjacent is going to be that -1 over the 2. Making this our square root of 3, one that we like. Which means this is our, in terms of degrees, it's a 60. In terms of radians, it's a pi over 3. But the angle that we really have is this guy. That is our y value right there. The angle to get us to that point. This is just our reference angle. So the angle to get us there is almost all the way to pi. So we're pi over 3 short of pi. Or our y is going to be 2 pi over 3. I like to think of pi as, in this case, 3 pi over 3. Getting that common denominator, 1 short, would make it 2 pi over 3. Let's do an inverse cosine of 0. So I'm asking myself what angle gives me a cosine of 0. And this is going to be one of those coordinate angles. And this is where you're going to try to remember one of 3 ways. You remember either the graphs, the collapsed triangles we've talked a little bit about in my videos, or the unit circle. So where in the world is that cosine equal to 0? And the answer to that is pi over 2, or 90 degrees. I think of the graph. There's where it's 0, right at pi over 2. My head has so many different facts floating around in there. Or if you're thinking the unit circle, cosine is your x value. X has to be 0. X is 0 on your y-axis, so we're up at pi over 2, 90 degrees. All right, let's take a look at the inverse tangent function. So we will get to the inverse tangent on this guy in this graph in this video. I will come back with one more video to kind of discuss some more difficult problems. Okay, but that'll be another video. So tangent function, y equals the tangent of x. And this curve actually shows up quite a bit, especially in the inverse when you go into calculus class. It does show up, which is really kind of strange, but it does. But it has some really cool features, but that's the math person talking to me. All right, so we have to remember what the tangent function looks like. Okay, that's the one with all these little asymptotes. And the asymptotes are at negative pi over 2. We have one floating around at pi over 2. We have another one floating around at 3 pi over 2. We have zeros at pi here. Kind of looks like this, and like this, and it repeats itself. Okay, and so again, as we've done in the past, we need to restrict our domain. So the regular tangent function has, for a domain, it's kind of hard to write. It's all real numbers except the odd factors of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, because that's where all those asymptotes are. So the domain is very hard to write. Our range is all real numbers. We get everything out because it goes from negative infinity all the way up. And this is when they could have chosen a lot of different places for this to create the inverse function. And the inverse function, we could have restricted it, from 0 to pi. Here's this piece and then this piece. But that's not the typical restriction that they look at. Where they do restrict is very similar to the sine function, from negative pi over 2, and I'm going to put a round bracket, sorry, to pi over 2, because those are not in. So we're going to be looking at just that piece. And if we do that, we still get our range. So there's our domain, restricted domain. The range is still negative infinity to infinity. So if I go to draw this inverse function, these vertical asymptotes, and this is the cool part, become horizontal asymptotes. So here we have a function that has 2 horizontal asymptotes, one up at pi over 2, and the other one down at negative pi over 2. And the inverse function kind of looks like this. There we go. So this would be y equals the inverse tangent of x. And I think that's a cool function. I don't know. It's just the math person in me. A function with 2 horizontal asymptotes. How cool is that? I do not believe there is a function that would have 3, because it would have to be a function, and horizontal means that as you go towards infinity you get close to one value, so you can only go to one value on one side and one value on the other. So this is the most you can have as far as horizontal asymptotes go. Alright, let's do some problems with the inverse tangent to be complete. And let's calculate the inverse tangent of, and I like to pick on this one, this triangle. So we're going to have that inverse tangent of a negative square root of 3. So again, that means we're looking for an angle in which the inverse tangent, or the tangent, is a negative square root of 3. Remembering our restrictions. Inverse tangent and inverse sine are restricted to the fourth and the first, the fourth written in the negative direction. Inverse cosine, first and second. Again, it just takes time to remember. That's why we kind of show you the graphs so you can get a better understanding as to why we restrict where we did. Tangent is negative down here. Tangent is opposite over adjacent, so I'm going to need to write that as a fraction. Negative square root of 3 over 1. This is my favorite, 1, 2 square root of 3. Woohoo! This happens to be a 60-degree angle. I was hoping you guys could get it in there in that pause. 60 degrees, which is our pi over 3, but we're in that fourth quadrant in the negative direction, so we get a negative pi over 3. So hopefully things are starting to click a little bit more. We're going to come back with one more video, and we're going to talk about combining some of these things a little bit and some of the more difficult type problems. You've seen them in Chapter 5. Some of them were a little bit tough. Some of you guys just skipped those problems altogether. But we're going to come back and do them again. And hopefully by having seen this again, it's going to start to click more. So we'll see you in the next video.